I'm going to talk to you about some work that we've been doing under the Human Architecture team and leveraging some of the efforts that are going on with Tim Glotch's RISE survey team, but we've also interacted with and have participation a little bit from David Kring's team. Dan Britt's team's been working with us. But we're basically, you've heard a lot of different talks today, and I really enjoyed also the talks from the European Space Agency folks yesterday on teleoperations. We're trying to do is understand how teleoperations might play forward into missions that are in planning now. Just real quickly, one thing we've learned is that if you have 10 people and you ask them about low latency telerobotics for a mission to another planet, they tend to have 10 well, maybe not completely, but somewhat different visions on how low latency telerobotics is actually applied to the architecture that they're thinking of. So this is just a quick display about what the trade space might look like. We can compare against things like our high latency missions to other planets, where we operate rovers with the comm delays, and we do a pretty good job. And we've learned a lot of lessons about how to maybe do that a little better, and what could we do if low latency were applied in those cases. On the other end of the spectrum, you kind of have the on-site presence, which is an example from Apollo. So the human dexterity on site is very high there compared to low human awareness, human dexterity, and a high latency type of mission. So what we're really talking about is this trade space between those two possible end members. And we're trying to understand what that trade space is really like. So many have stated that low latency could be beneficial to scientific exploration. We want to ask the question about how do you envision the low latency being applied? If you think about a z-axis on this thing, what we really want to do is figure out the situation in which we maximize the science return that we could do in a mission. And so that's what we're trying to understand, and in general, this is a relatively unexplored area in the trade space for NASA. Now, another way to think about this trade space in a little more detail was presented by the Human Science Objectives SAG for MEPAG a little while ago. We did this in 2015, and we put together this chart for a range of style human-robot interaction / control. So here you have types of interactions. You could have robotics and crew working together. How this is operated could be from site, from home. You could have them working at the same place but not necessarily together, or handing off tasks to each other as they move along. You could also have robots acting completely independently of the humans. And you can think of a range of how those robots could be controlled. And the other part about this is they don't necessarily have to be controlled in that manner the entire time. The manner in which they're controlled could be handed off in different scenarios. Crew members on a different planet are going to need to sleep. Do the robots need to sleep? Not necessarily. They could be handing off control to other folks who could be running them at that time. So folks in this room that don't study Mars may not be as familiar with the squid chart, as it were called, but this is the journey to Mars. But for this community, we could say this is journey to or nearby the airless bodies that Survey's interested in studying. So the main point here is there's a plan for eventually getting humans to Mars. And it's this, as Jim has talked about, this synergy between all these different aspects, science, exploration, technology. But the important point is that on the path there, we may be passing asteroids. We may have time in the space in the lunar system. We may be encountering the moons of Mars. This is another graphic that works through this. Again, this is what we're calling the proving ground. And Jack gave a little presentation about one of the studies that's coming up, and I'll bring it up here in a minute as well, but the HEP-GSAT is starting to think and rapidly trying to think about how are we going to do operations in the proving ground and what is it we want to get out of that. So in the Human Architecture team low latency telerobotics study, the idea is that low latency from Mars, from either the moon's or orbit to the Mars surface, could be used to operate assets, either prior to human landing or to go into places that humans are basically forbidden from going into because of certain protections on those sites. So we do run into those types of things there on Mars. So there's certainly a number of ways you could envision using low latency to operate robots in that system along with humans. So the point of our study is not necessarily a design reference mission. We're not trying to design and plan exactly how a low latency telerobotics mission would be run on Mars, but we're beginning to try and explore the best practice for using low latency telerobotics. The big question is, between now and whenever a mission like that might happen, there will be a certain amount of finite investments that can be made in technology development. What we want to do now is start defining the questions that we can test and figure out where to put that money. How do we invest that? If we're going to invest in low latency telerobotics, how do we want to invest in low latency telerobotics so that we maximize or enhance the science that we're done? And the point for Survey is that this can and most likely will involve the proving ground, which means the moon and or asteroids and or the moons of Mars. So just a brief background about where some of this work came out of. In 2012, Goddard held an exploration telerobotics symposium, and this generated a report that was given to League later that year. This brought folks from industrial groups that do deep sea exploration, mine exploration, folks that are doing low latency work here on Earth right now. They came in and briefed this community of the NASA community on how telerobotics is applied currently in exploration of the Earth. This was followed later by a technical interchange meeting between multiple centers across NASA and trying to develop a plan for how and if we wanted to invest in low latency telerobotics. Jack talked a little bit about this, so I won't go into much detail, but we got to the point where we were actually testing low latency telerobotics from the ISS to right here at Ames Research Center, deploying assets with telerobotics capabilities. So we know that we can do it. If you saw the talks yesterday, ESA's carried this torch forward a little bit farther, and they're continuing to do that. I'm really happy to hear about that. And hopefully we'll keep doing this. And again, one of the things we want to do is make sure we're asking the right questions so that groups like ESA that are currently doing these tests can work with us and work together to test the right things. MEPAG had the Human Science Objective SAG. Again, that's where we talked about human-robotic collaboration. Jack also talked about the League HEP-GSAT that's ongoing right now. So this is where we're starting to define the science that could be done in the proving ground in relation to in what I'm talking about today, low latency. Later this year, there's a Keck Institute Space Science Low Latency Telerobotics Workshop that will be held at JPL. So if you have thoughts on what might be discussed or just in general about how low latency telerobotics is applied, be happy to listen to it and try to make sure it gets into that test. So telerobotics studies, what does low latency telerobotics mean? Well, again, if you ask 10 people, you might get 10 different visions for how low latency works within a human architecture. Right now, we have very well designed high latency, what I would call high latency telerobotics, although Tony just talked about operating resource prospector and what would be closer to a low latency operations mode. So we're working on merging these concepts right here, but this is what we're dealing with right now. For the sake of our study, a key observation that came out of a lot of the studies on the prior slide is state-of-the-art NASA instruments work well within a high-latency telerobotics operational framework, but not necessarily low latency. If you're going to send people the whole way to Mars to operate a rover really fast to make a measurement that takes 10 hours to complete, that might not be the best scenario for using low latency. And this is where the question comes up, where do you apply low latency? So again, we're evaluating, in this case, the impact of low latency telepresence to the overall timeline. So unlike robotic missions where you can get an extension if the instruments are kind of working and most of the wheels are still working, you could keep extending the mission and doing more science. The humans are coming back. So they're not probably going to extend missions that have a finite amount of resource to keep humans alive. They're coming back, which means you have a start and an end date in time for a low latency telerobotics mission. And so the question has been posed, how much can you actually complete with a low latency telerobotics paradigm stuffed into that finite amount of time to complete? So when you start adding up the time that it takes crew to stay alive, keep their spacecraft operating, deal with potential problems, other scientific experiments, exploration experiments, how much time's left for this kind of science and how much can they actually complete? Okay, so Mike Wright, one of the co-authors on this abstract, has a much longer talk about this, and he gave it also earlier this week. I'm going to show you these slides simply to point out Again, we're not trying to do a DRM or anything here. What we're trying to do is assess the timelines. And so what I have here is an example. In this case, we go the whole way back to HEMSAG in 2008. They did studies like this. The first one we went to was Centauri Mons. So we're not going to recreate these tests. We're just going to use what's already on the books. And so what we did was follow some of the traverses that they worked on. What we came up with, based a lot on the prior studies, is for a first order, let's divide some of the faster operating instruments onto one rover and some of the slower operating instruments onto a different rover. So now we have dual rovers, one that can operate faster than the other, and we'll see how that applies to a low latency paradigm. So what we did was we broke down potential instruments and started adding up the time. How long does it take for those types of instruments to make measurements now? If we can start making some guesses at how quickly they might operate in the future, we started working that in. We started building it. Now, any one of you could shoot holes through this all day long, and that's fine. We're not doing a DRM here. What we're trying to do is start understanding where the choke points in the timeline might be, because those are where the investments in telerobotics could be made now to try and help us work better. So this is just an example, again, of how the sampling rover, we had a low latency rover, we had a higher latency rover that would interact more directly with the samples on the surface and make measurements. Again, trying to get at bigger questions, in this case, about life on Mars. So, an example of one of the conclusions that we reached. The question was asked to us, if you had 4 crew members in orbit at Mars, how much of their time is needed to do science operations? So once again, some of their timeline is dedicated to many other things related to keeping humans alive in orbit or on the surface of the moons of Mars. The time that is allocated to them to do science, how much could they complete? So by stacking the time up to complete all those measurements, do those types of drives, we start getting at things like this. If we were using the two rover idea, we thought that maybe you would have a science lead who's dedicating their science time 100% to the rovers being in operation. The other 2 rovers might not have an entire 100% of time dedicated from an individual crew member. So of the 4, maybe you have a science PI who's in charge of understanding the data as it comes in. Again, we have a science team back on Earth that's also doing that. But the idea of low latency is that you have a quick response time. Somebody needs to be keeping track of that data in real time. That's probably a full-time job. Driving the 2 rovers, some of which are sitting for long periods of time to make their measurements, that can be handed off. So those crew members might be coming in and going based on what the science PI is saying. Now again, you could sit here and question whether that's accurate in your mind of what low latency telerobotics might be in the future, and that's totally fine. We're okay with that, and we would love to have discussions. Mike is in the back of the room. Talk to us anytime you want. The real questions, though, are, as you stack all that time up, maybe you don't get as much done as you thought you could. Where are those choke points in the timeline? Is it the instruments? Are the instruments taking too long to make the measurements? If that's the case, maybe we need to be investing in making instruments that work faster, that collect data faster. Maybe we can envision synergies between rover types and operation of the rovers. Humans on Earth doing some of the tasks that take a while to do, while the crew members are focused on other things. But, for instance, if you find a sample that's of high value but is very dependent on exposure to the atmosphere, then you might want those crew members to swoop in and use their low latency capability to collect samples and make an informed decision in real time before they're altered. So again, the question here is about starting to define the right kinds of questions that could be tested by groups like Terry Fong's group here in operating low latency rovers. We're not designing the reference missions ourselves, but we're working on what's been provided to the community already. Thank you.
Perfect. You're ahead of time.
Okay, so we have one more talk.